Hello, hello.
Hey.
Welcome. Um, if you are just tuning in, I'm Jordan and this is Nathan, my co host. And our next segment here is going to be hosted by our friends. Would you like to introduce yourselves?
Yeah, sure. Saurabh here. I'm product manager for SageMaker Inference.
Hey everyone, I'm Vikram Ilango. I'm a machine learning specialist SA. I'm joining the show from Herndon, Virginia. Excited to be part of the show, and I'll be showing a demo of our new feature MME support for GPU.
Awesome.
Okay, so SageMaker, I know that the SageMaker is offering a lot of different tools for working with machine learning and creating machine learning models. Tell us more about what you in specific are launching today.
Yeah, so early this week we launched MME, which is the multi-model endpoint support for GPU. That allows customers to deploy thousands of GPU-based models behind a single SageMaker endpoint and reduce cost up to 90%.
Okay, so I know SageMaker has endpoints, and I believe I had heard something about multi-model before. What's different about this multi-model?
Yeah, so previously our multi-model endpoints were only supported for CPU, and we've had like a lot of customers love it. Like, it gives you the cost savings by allowing you to carpool the resources across all the models that you're deploying. And the usability is also very simple, right? Like, so you just throw in all your models at an S3 location, register that S3 location, create an endpoint, and start hitting with your target model. Behind the scenes, we're going to kind of dynamically load and unload models, trying to give you the best price performance, right? So it was working very well in the CPU world. We had like a lot of customer interest on like, hey, we want this for GPU as well, because like once you're training like these deep learning models and want to kind of host thousands of models, like cost can just add up, right? Like, so yeah, I mean, it was a long awaited launch.
That makes a lot of sense. So I mean, I can imagine, if I want to run a model, dynamically on demand in response to, some event happening or some data coming in, I have to choose some way to host that. And if I was using like a traditional EC2 and I have thousands of models, what is that going to end up looking like? Am I going to have like thousands of EC2 instances running? Like, how does this improve on that situation, make it easier for me?
Yeah, so in SageMaker, we do have like a variety of options that customers can choose from, right? Like we have real-time endpoints that allows customers to kind of host one model behind one endpoint, kind of access them in a low latency fashion. We have asynchronous inference, kind of which lets you have near real-time latencies to get your inference back. We have serverless option, which like where you could basically get a serverless endpoint and pay as you go, right? And then we have a batch inference where you basically give us a bulk of your data, kind of bad job runs, and you'll get your predictions back, right? But in the real-time endpoint, that's where like customers are kind of really cost sensitive as well as like latency sensitive, right? Like, so to going back to your example, if you were to use like a real-time endpoint and you had like 10 models, you would essentially be creating 10 endpoints, kind of provisioning, let's say 100 instances behind each of the endpoint, and kind of and kind of planning a little bit for your buffer for your kind of peak in your traffic, and then kind of invoking them and as you get it, as your traffic comes in, right? But like imagine like from going from 10 to 100 or maybe 1,000 models, right? Like costs could just add up, and yeah, I mean, at some point it makes sense for you to kind of just carpool the resources, maybe have like 100 instances provisioned to host thousands of your models, and let SageMaker kind of do the model management and the heavy lifting to kind of dynamically load and unload models.
That's interesting because it sounds like there's kind of two ends to it. There's like this fully serverless spectrum where I'm just provisioning a serverless endpoint for one model.
Yep.
And then there's kind of the fully like self-managed option, which is I'm choosing an instance and I'm saying deploy this many instances of this model on this endpoint. It sounds like this is somewhere, if I'm understanding correctly, in the middle between the two. Like it's doing some smart magic to take a pool of instances and say, I know how many need to be dedicated to each model, but I'm sharing that capacity.
Exactly. So if you think about it, right, like, so you have the real-time endpoints on one end, like where you're basically kind of getting the lowest latency and kind of hosting the models that you'd like on dedicated instances, right? Like, and then you have serverless, where you're basically going like just creating serverless endpoints and only paying when you invoke it, right? And then there's like MME in the middle, where you're essentially provisioning an endpoint, right? Like allocating certain number of instances behind it and saying like, hey, host these 1,000 models that are in S3 bucket or whatever, like hundreds of models or like up to 10,000 models or something like that, right? And then just kind of invoking as you get traffic, paying for only the instances that you've kind of provisioned, and leveraging like the smart dynamic unload we have. Also, uh, I actually forgot to mention about the smart routing. So we do have like smart routing, which also kind of understands your traffic pattern over the period of times and tries to make sure that we have those models that you frequently invoke always or near always in the memory, and kind of the ones that you don't invoke so often kind of kicked out as and when we don't see them being called, right? So the smart routing kind of becomes smarter as you keep sending your traffic, and for the models that you have been invoking in a short term window and a long term window, you'll not incur those kind of cold starts that you would otherwise incur because we are dynamically loading those models. So yeah, I mean it's a good way to strike balance between like being on the serverless side of the spectrum and on the real time endpoints where your cost can just add up, and especially with GPUs like and deep learning models, like customers kind of tend to have like uh, like of course training is expensive, and when it comes to inference you're dedicating those instances, and it's long running endpoints. So a good cost saving option with that for those customers.
Yeah, it's nice that you can kind of maintain some of the flexibility of, kind of the DIY approach, but also getting the benefits of serverless.
Yes, yeah, true.
Yeah, so we've actually got a question from the chat, which is about the VS Code integration with SageMaker. And they're asking if it can be used to launch custom Docker containers to do development for, say, Lambda, local, glue, local, that sort of thing.
Sure. I can take this question. SageMaker Studio is our integrated environment for end-to-end machine learning. So you have an IDE, and developers, data scientists can onboard to SageMaker Studio, and you have the flexibility of having a dynamic compute instance behind the scenes. So you can seamlessly switch between different compute instances, and you have a development environment which is similar to a Jupyter server. We are improving our SageMaker Studio, bringing more IDE capabilities to it. And you can also develop custom Docker containers and host it on Amazon Elastic Container Registry. That's our container registry where you can push your custom Docker images, and you can use that with SageMaker, different capabilities within SageMaker, like SageMaker processing, training, and even for inferencing, you can bring your custom Docker images hosted in ECR.
And so this is the phase where you've already sort of built your model, you've trained it. Now you want to deploy it on the edge, and you want to actually run that model
right
now, perhaps in response to some sort of real-time data coming in, right?
That is correct.
Yeah, I think maybe the best thing for viewers to understand better about the place where this is to do a demo.
Sure.
I understand we have a demo to show, right?
Sure. I can jump right into it. So I'm showing a Jupyter notebook where I have created an MME endpoint, SageMaker multimodal endpoint. Let's take a look at what goes on behind the hood when you create a multimodal endpoint. So we are seeing a multimodal endpoint with two instances, which is powered by GPUs. In our demo, we'll be seeing an NVIDIA T4 GPU instance type. And when you create that, we'll be using NVIDIA Triton inference container, and it has support for all major frameworks such as TensorFlow, PyTorch, Onyx, TensorRT. In this demo, we'll see a couple of framework-based models. One is PyTorch and a TensorRT model. And as Saurabh mentioned, SageMaker takes care of two important heavy lifting for our customers. One is smart traffic routing and fully managed model placement. What do I mean by that? For the first time when the model is invoked, say, for example, model 1, on the right, we have our S3 where our models are hosted. SageMaker downloads the model dynamically from S3 onto the container instance, and then load it onto the container memory and serve this model. Smart traffic routing. So when a request comes for model 2, SageMaker is aware of the model is placed in 2 different instances. Here in this case, model 2 is on 2 different instances, and SageMaker smartly routes traffic to the instance that's not being actively being used. Fully managed model placement. So SageMaker is aware of the traffic pattern that's coming to the endpoint, and model 2 is being invoked more frequently. So SageMaker made a copy of model 2 and placed another copy of model 2 on the instance 2. Say, for example, model 3 is not being frequently used. SageMaker makes a determination to take take it down from the container memory so that it can free up the memory, GPU memory, for more frequently used models. All the models are effectively sharing the GPU core, and the model copies are optimized to give the best price performance in this case.
So what happens if I have one model which is just gigantic and it would completely consume the resources of a whole GPU?
Right.
Does it handle that situation as well?
Yeah, so MME can horizontally scale. Say, for example, if one of the models is huge, you can adjust the number of instances behind your shared fleet. You can add more instances, and based on the traffic that's coming in, based on your invocation or your GPU utilization, if a model is huge and it is using up more GPU units, you can additionally scale your MME endpoint, have more instances, and serve more models that way. So auto scaling takes care of that.
Super
Yeah, adding to that, Nathan, I mean, it's not like for every instance that you've provisioned behind the endpoint, right? Like we have the same model. Like we treat the entire pool of instances that are provisioned behind the endpoint as a pool that where we can place models, right? Like, and we'll try to kind of place models to give you the best price performance. So let's say, going back to your example, like if there's a large model, we'll basically try to place it on an instance which probably has the space enough to accommodate that model, right? Like, and while if you have like a bunch of small models, we'll try to bin pack as many small models as possible on some other instance, right? So we'll take care of that smart model placement on the top. So you're just invoking the endpoint with your model name without worrying about how those models are being placed on those instances and
That seems incredibly useful because now I no longer have to worry about I'm going to pin this model to this particular GPU and then this machine over here I'm going to pin this one, and manage allocating GPU cores to particular models and processes.
Yep. And I want to call out, like we've been working on this project for almost year now and collaborating with NVIDIA. So we've worked this out with the Triton team to kind of get the best customer experience out, where like customers don't have to worry about, as you were saying, like, hey, this model runs and is attached to this GPU, and then like they have to worry for thousands of these models.
Continuing with the demo, we'll see a computer vision use case where we'll be using a ResNet 50 pre-trained model. The first step, when you want to host a model with MME, you can train this model on SageMaker, on EC2s, or even on-prem. You have to create the model artifact so that SageMaker can host these models behind the MME. So in this case, we have a PyTorch model and also a TensorRT model. So Triton expects the model artifacts to be in certain format, which is in the model repository. In this case, we are seeing ResNet as the model name, and underneath it, we have one as the version, and model.pt is the model artifact. Also, we define the model configuration, which talks about what's the input and output going into the model and coming out of the model. Also, we need to make sure that we specify the platform. In this case, it's going to be the PyTorch backend platform. TensorRT is an SDK for optimized deep learning inference. So it has a runtime and an optimizer that can effectively tune your model for best latency and concurrency. So we take the same ResNet 50 model, first transform it into an ONNX format, and we use TRT-exe, which is a command line utility to create a model plan, TensorRT model plan. TensorRT, what it does is it does few things behind the scene. It can dynamically plan the memory, so it can effectively compress the memory of your model and make more effective use of the GPU. Also, it can do quantization, it can bring in precision calibration, and memory fusion and layer fusion and so on. So you, by the end of the process, you'll have an effective engine that is optimized for your deep learning inference. So once we have the models that are ready, we need to upload it to S3 so that MME can read those models from S3 and serve the traffic that's coming in. Next step, we right now we have all the models, both the models loaded in S3. We'll go about defining the container specification for multimodal endpoint. In this case, we specify the model URL, that's the S3 location where all the model artifacts are stored. And we specify the mode as multimodal, which gives the container an indication that we'll be using this in a multimodal fashion. We go about creating the model, and we create the endpoint configuration. Here we are using MLG4DN X large, which is powered by NVIDIA T4 GPU type. And we have initial instance count as 1, and we also can see the auto scaling later in this section. We create the multimodal endpoint, wait for the instance to come up, and now we are ready to serve the traffic using MME. I'll also go a little bit into the auto scaling aspect. So you can dynamically adjust the number of instances behind your endpoint depending on the traffic that's coming in. Depending on invocations or your GPU utilization, you can adjust the number of instances behind your endpoint and serve any spiky traffic that way. So now we are ready to pass in a payload. In this case, it's a image classification task. We'll be passing in an image and see what the classification is. We have a bunch of helper utilities that can transform your data. Here we are first passing in an image of a dog to the TensorRT model. So like I mentioned, we have two different models behind MME right now, and I'm passing it to a TensorRT model. In this case, the model identified this particular picture as a Shiba or an Alaskan Malamute type of dog. We also can send another image to the PyTorch model. In this case, we send a cat image and we see what the model predictions are. In this case, it identified it as an Egyptian cat. It was more specific, not just a cat. The model was able to identify it as an Egyptian cat. Just before the show, I simulated more and more models just to show the capability of MME. And CloudWatch gives an idea about what's happening behind this multimodal endpoint. So at that point in time, I had more than 16 models loaded, and I can see the utilization of the resources during the invocation itself. A couple of metrics that are interesting here is the GPU memory utilization. At this given point, when we had 16 plus models loaded behind this MME endpoint, the GPU memory utilization was around 42%. The memory utilization was around 20%. This gives an idea about how many more models can this be accommodated, and also in invocation level metrics. So how many invocations are coming per instance, and what's the latency of the model. So in this case, the model latency is 1.32 seconds. The overhead latency is around like 690 milliseconds and so on. So this gives you an idea about both the invocations and the instance level metrics. So with this new feature, rather than having 17 different endpoints to host your models, we have one instance to host all the 17 models. So that's the type of cost benefits and cost realization that our customers can benefit from.
That's really fascinating. I like especially seeing the latency aspects there, because one of the classic aspects of serverless is the cold starts. Like, if you're going from 0 to scaling up, there's going to be an initial delay where we'll have to set up the model. But it looks like this allows me to have a little bit of the best of both worlds. Like, I don't have to think so much about the capacity,
right,
but I can be confident this model is already loaded up somewhere in the cluster, and it can scale up, as needed on the fly.
Yeah, and I want to also add, like even when you're setting auto scaling policies, there's no, like, you're not setting auto scaling policies for 17 models if you have those, right? Like, you're just setting one auto scaling policy for the shared cluster.
So the auto scaling policy is just how much total capacity do I want to share across all of these models?
Yep. I mean, for example, like, you could be sharing, like, hey, if my overall GPU utilization of the fleet goes above whatever, like 70%, then throw another host, right? Like something like that.
Very nice. I like that.
Yeah.
Um,
And one more
so
thing I want to call out is typically like the use cases we're seeing as part of amongst the customers who are interested in this feature is they want to train like hyper personalized models where like let's say they're training like a model specific. You're a ride sharing company and training a model specific to every city. Maybe it's your pricing model or personalization model or something like that, or you're a SaaS and ISV customer who's kind of training or building AI for your own customer, right? Like let's say you have 1,000 customers, you want to kind of build a custom AI for each of those customers, but are looking for cost saving options to host that. MME is the way to go. And another interesting thing, since we're using Triton, is you could be having an MME endpoint, but using like kind of different model frameworks, right? Like so in deep learning, you have these different frameworks like PyTorch, TensorFlow, TensorRT, and Onyx, and stuff like that. Uh, like typically, you would create like a dedicated endpoint for each of those. But with Triton, like they offer like a multiple framework support, and since MME on GPU works with Triton, you could essentially kind of have models which are using different frameworks hosted behind the same endpoint with MME.
well, this looks very, very good, and I think that's a fantastic use case as well. I'm sure viewers are going to be very excited to try this out.
Yeah,
So thank you so much for demoing this for us today.
thank
We
you.
do have another SageMaker segment coming up back to back, so
Double
we're gonna have
SageMaker
to transition
special.
over to that one.
Yeah, before we drop off, Nathan would like to highlight Vikram is having a workshop at reInvent. So, folks who are watching, feel free to drop by at AIM 401. It's on Friday, 8 a.m. So, see you at reInvent.
Awesome! I'm looking forward to seeing you there at reInvent too. Thank you.
Thanks, everyone.
Thank
Thanks
you.
for. Thanks.